Thanks for being here. My name is Marco Eilers. This is joint work with João, Isaac, Patricia, and Peter, and we're all from ETH Zurich. So the topic of the talk is modular reasoning about global variables and their initialization, and I'll give you an example what we mean by that. So here's a Java program. We have a class byte that has a static field called cache. So this is Java's version of a global variable. And now what's also in this class is this static block. So that's an initializer block that, if you look at what it does, it allocates an array and allocates a bunch of byte instances and places it in the array. And now this initialization block in Java runs lazily. So what that means is at runtime, if I run this client code at the bottom, for example, the moment I first use the byte class in any way, for example, I read this cache field here, at runtime, trying to read this field will trigger the initialization of the class. So that means I will actually jump in my execution to this initializer block. It will run until completion. At the end, we return, and then we actually perform a field read, and we get the array that was just allocated. So this is a typical use case of initialization of global state and static initialization in Java. This code actually exists basically like that in the standard library. And generally, like typically, global variables and code related to it is a small part of a code base. But of course, if you have any substantial amount of code, probably you're using it somewhere. So if you want to verify your code, you have to be able to reason about it. So this was a Java example, but of course, other languages have similar concepts, whether they're called static fields or global variables in C, C++, and Go. Roughly, we have two big groups. Those where initialization happens lazily, like in Java. That's also the case in C# and Scala, for example. Or those where initialization happens eagerly. So these initializers run before the main function is called, which is the case in C, C++, Go, and others. What these have in common is that reasoning about when the initialization happens is quite difficult. So in the left group, that's the case because this initialization order is actually determined dynamically, right? Because it happens on the first access to the class. But it's also difficult in the right group because in all those languages, the order in which initializers run actually depends on the compilation order. So on the order in which you pass different files to your compiler. So that means in all these cases, the initialization order and the exact time on which initializers run is not known modularly. So if you implement a library that uses static code, you do not know exactly when and in what order your initialization code will run. So our goal in this paper is to solve this problem and to find a way to do modular language-independent reasoning. So reasoning that works for all of the languages that I've mentioned before, whether lazy or eager, about global state and its initialization in the setting of concurrent separation logic. And our basic approach, our central kind of specification instrument, is what we call module invariance. So what a module is depends on the language. In Java, it would be a class. In Go, it would be a package. In C, a compilation unit. But the point is that a module invariant describes valid states of your global state. So if we go back to the byte class, we want, as a first constraint, that the initializer always has to establish the module invariant. In the byte class, we would say, well, the cache field can't be null, and the array has a specific size, and it contains the right values. Right? So we have, as a first proof obligation, that the initializer has to establish this invariant. It has to hold at the end. And now the second and super central aspect is that clients should be able to use this invariant without having to reason about when exactly initialization happened. So as I've just said, doing that modularly is very difficult or impossible in these languages. So if a client wants to use an invariant, it shouldn't have to reason about when exactly initialization happened. Instead, it should prove some set of sufficient conditions that together imply that the invariant must be holding at this moment, no matter when exactly initialization has happened before. So if I have a client like this, I want to prove some set of proof obligations that together imply that the invariant holds now. And then the key challenge is, of course, well, what are these proof obligations? When exactly is the invariant of some module guaranteed to hold? And this is what I'll answer in the rest of this talk. So At a basic level, we have two central proof obligations, right? We know that an invariant of a module will hold if the initialization of that module has finished, so the invariant has been established, and also the invariant is not currently broken by someone else. But as I've already said, proving this left condition modularly is really, really difficult. So a central contribution of the paper is that we've identified two other conditions that together imply that the initialization has finished, that we can actually prove modularly. And those are these two. So we proved that initialization of a module must have started at some point in the past, and that the initialization of the module is not currently ongoing. These are two conditions that we can prove modularly, and I'll show you how in a second. And together they imply that the initialization of a module must have finished. So those three will be our central proof obligations, and I'll walk you through those. So the first one is we must prove that the initialization of a module has started at some point if we want to use its invariant. So if we go back to the same example as before, then this is actually super easy to prove. If we want to verify our client here, we can prove that initialization of the byte module must have started at the point where we try to read the cache field because we're trying to read the cache field. Right? So if we're in a lazy language like Java, then trying to read the cache field is actually what will trigger initialization if it hasn't happened before. If, on the other hand, we're in an eager language like C, then initialization will have happened long ago before main was even called, right? But in either of these cases, we know that at the latest, when we try to read the cache field, it will have started. And we represent this fact through an assertion that we call an init fact. So init m of a module means at some point in the past, initialization of m has started. So this is the first thing you have to prove if you want to use a module invariant. The second one is what I've mentioned, initialization is not currently ongoing. So concretely, what we have to prevent is this scenario. So it's the same byte class as before and the same client as before, but we have on one additional line. So now from the initializer of the byte class, we actually call the client. And if you think about what happens in this scenario, if we execute this, right, the client will be invoked, but at this point, the invariant hasn't been established, the cache field is still null, and this will actually crash. So in this scenario, it would be wrong to assume that the invariant holds here because it doesn't yet. So this is what we need to prevent. And our way of doing this is a system of what we call initialization levels. So initialization levels are values from some partial order. Here I'm using natural numbers that are associated with every module, every initializer, every method, every procedure. And now these levels have to satisfy some constraints that we can check modularly. So the first one is every module's level has to be greater than that of its initializer. Then we have general rules that ensure that if, for example, we have a client, the level can only decrease with calls. It can never increase with calls. So if we have this potentially dangerous call here to the client method from the initializer, then that introduces a constraint that the initializer's level has to be greater or equal to the level of the method that we're calling. So far, we've the levels that I wrote there satisfy all these constraints. And what these two constraints give us is essentially that whenever our current level is greater than that of a module, it can't possibly be initializing. Right? Any execution starting from the initializer will have a level lower than that of the initializer. So that means now in the client, if we want to use the invariant of the byte module, we can show that initialization, or try to show that initialization isn't currently ongoing by showing that our level is greater than that of the module. And this constraint doesn't hold here, because we're actually being called during initialization, and this is why we would reject this example here. Okay, so this overall system gives us a second proof obligation. Our current level must be greater than that of the level whose invariant we're trying to use. Then we have the last proof obligation, which is that the invariant is not currently broken by someone else. And it could be currently broken by someone else in essentially two different ways. First of all, it could be broken by another initializer, right? We could have this disrupt module here that has nothing better to do than set our cache field back to null. So we prevent this by generally controlling side effects of initializers. Because we're in a separation logic setting, we're just doing this via ownership. So when we verify module initializers, we prove that they're correct in a setting where they only have ownership of their own global variables. So the disrupt module here, its initializer is only allowed to access its own global variables, of which there aren't any. And the byte module's initializer is only allowed to access its cache field and no other global variables. And that rules out this disrupt class here. And then there's a second way that the invariant could currently be broken, and that's not broken by some initializer, but just by other code. For example, we could have this client caller here that calls our client in a state where the invariant is temporarily broken. So again, in the client here, it would be wrong to assume that the invariant holds. So for this final problem, we introduce a notion that we call module tokens. So that's a separation logic resource that essentially represents the right to use the invariant of a module at the current point. So initially, these are all given to the main function, and the main function can then pass them around in the program. So if I finally want to verify my client code here, what I would have to do is first of all give it a precondition that says, if you want to call this, you have to give me the token for the byte class. And now I have the init fact for the byte class, I satisfy the level constraint, and I have the token. And these three things together, I can now exchange for the invariant of the byte class. And that now gives me ownership of the cache field and tells me that the field is not null and contains the right amount of values, etc. So now I can read the field, I can change it if I want to. I can exchange the invariant back for the token afterwards if I want to. OK, so that's the basic idea. In the paper, there are more things. So we have a notion of duplicable module invariants that are never broken after they're established. For those, we don't need the token. They're useful for read-only state. We also talk about solving a different problem, which is initialization cycles that I haven't mentioned here. We formalized this whole thing as a concurrent separation logic based on Eilers and proved it sound in Rock. The formalization is quite interesting. If you like this kind of stuff, you should have a look. We've implemented the technique in two different SMT-based verifiers, in Vercor for Java, which is lazy initialization, and in Gobra for Go, which is eager initialization, and verified a bunch of small case studies. And arguably more importantly, we've integrated this technique into a larger verification effort of real-world Go code base. So this is 5,000 lines of Go code that constitute a router implementation verified in Gobra, and that uses global state, and where previously, essentially, there were unjustified assumptions. Now we use our techniques to have sound reasoning about this global state. So to conclude, I showed you the first modular verification technique for global variable initialization. It's based on concurrent separation logic, applies to a wide range of languages because we abstract over the exact initialization time and semantics. We proved it sound in Eilers, implemented it in Vercor and Gobra, and of course, all of this is in the artifact, and you can check it out if you want to. Thank you.
Do we have any questions?
Can you say a couple of words about how the verification conditions that you create differ in a native language and in an eager language? And in other
So the technique is language agnostic, and you can use exactly the same verification conditions in a lazy language and in an eager language. So there's one logic that works for both, because we're only making like a set of very basic assumptions that are true both in the lazy and in the eager languages. Like that, for example, initialization starts at the latest when I read the field, right? That's true in C and in Java. But in the implementations in Vercor and in Gobra, we actually incorporated some additional knowledge, right? Java does give additional guarantees beyond our basic assumption, and so does Go. And so there we can actually skip some proof obligations that exist in the logic because we know from the language that they're always true, or we just have additional guarantees from the language. So there's one base logic that covers all the cases, but then you can incorporate additional language-specific like knowledge if you want to.
Let's do the laptop switch here. Was that another question? Okay. Pick your favorite.
Relatively quickly, one point which you can curious about, so presumably not ongoing has started is the same as finish. You didn't actually have a condition that says the thing's initialized.
Well, the thing is initialized if its initializer has started and is no longer ongoing, right? That's those two things combined to it must have finished.
I'm just curious as to why you structured it that way.
Because those two things are things that you can actually prove modularly, right? The starter thing is easy to establish, and the not ongoing follows from the levels on the call graph. It turns out that like directly proving it's finished is just really, really hard. So this was a way that, in a modular way, right? Modularity is the key issue. So like essentially picking it apart into these two separate proof obligations was what enabled to do it modularly.
And the module tokens are basically a bucket, an abstract predicate for the...
You can treat them like that, yes.
Exactly.
Thank you.